We're now in a place where we're ready to see the definition of area. The area of a region that lies under the graph of a continuous function f is the limit of the sums of the areas of approximating rectangles. So we have r sub n or L sub n, it actually doesn't matter. And the expression inside the brackets is function height times width. We saw that 3 times here. And here what's saying is the limit as n goes to infinity. Look, these rectangles for L sub 6, say, were all too big. But suppose that I made rectangles that were half as wide. Then I'd have rectangles, yeah, they're still all too big, but they're less too big. Or suppose we used, instead of 12 rectangles, 24 rectangles, or 36. The smaller the rectangles that I use, the smaller the gaps are above, in this case, above the function, or below the function. And as n goes to infinity, an infinite number of rectangles, the left endpoint and the right endpoint, they basically become the same. And so here we're saying it's the limit as the number of rectangles goes to infinity of the estimate of the area obtained using rectangles. Now we're going to see how we can use the definition of area to express the area under a curve f. In this case, f of x is equal to x squared plus the square root of 1 plus 2x, where x is going to go from 4 to 7. Now, we have here the area is a limit as n goes to infinity of function times delta x, right? So that's height times width. We're actually, instead of writing down f of x1 times delta x plus f of x2 times delta x, we're going to go generic. Suppose I have an interval on the x-axis from a to b. And I divide it up into a bunch of subintervals, and I'm not going to say how many there are. We'll just say that there are n of them. A, I'm going to say, is x sub 0. And then we have an x sub 1 and an x sub 2 and so on. So I'm just going to dot it because I don't want to identify each one of these. I want something that's going to be more general. So f of x, or sorry, x sub I there. And then I'm going to dot. And then we'll say b is x sub n, indicating that we have n subintervals. The width of each subinterval is delta x. And we can compute how wide this is. In the previous video, we went from 0 to 12, and we used 6 subintervals, and so delta x was equal to 2. That's basically taking 12 divided by 2, but behind the scenes, it was really 12 minus 0 divided by 2. The point here is the distance between a and b is b minus a. And then if I'm going to chop that up into n pieces, I'm going to say delta x is b minus a over n. Now let's talk about these endpoints. X sub 1 is a plus delta x, the width of a subinterval. X sub 2 is that value, a plus delta x, plus another delta x, right? So a plus 2 times delta x. And you can see that x sub 3 would be a plus 3 delta x. There's a pattern here. X sub 2, a plus 2 delta x. X sub 3 would be a plus 3 delta x. So x sub I is equal to a plus I times delta x, which can be expressed as a plus I times b minus a over n, because that's our delta x. And in case you're wondering how this works for the right endpoint b, b is equal to a plus n iterations of b minus a over n. Guess what? The n's divide out. Guess what? The a's subtract out. B is equal to b. It all makes sense. Out of all of this, here's what I want you to have. That delta x is equal to b minus a over n. and that x sub I is equal to a plus I times b minus a over n. Okay. Now, I think I'm ready to express this sum using sigma notation. So we're going to say area is equal to the limit as n approaches infinity, right? So I am incorporating the limit there, of the sum as I goes from 1 to n. That's our x sub I, right? I goes from 1 to n, of f of x sub I, right? That's what's happening here with, well, really here, with f of x sub 1, f of x sub 2, f of x sub n, blah, blah, blah. And factoring out the delta x, we can write that as a delta x there. Now that's the expression I want to use to give the area for this particular function. Now we have that a is equal to 4. And we have that delta x, which is b minus a over n, is equal to 7 minus 4 over n, or 3 over n. X sub I is then 4 plus 3i over n. Our area is then the limit as n approaches infinity of the sum as n goes from 1 to infinity of 4 plus 3i over n quantity squared plus the square root of 1 plus 2 times 4 plus 3i over n. All that times delta x, which is 3 over n. There's a limit expression for the area described here.